Well, all right. Now it is. It didn't tell me that I'm. Oh, it does say I'm recording now. All right. So we're gonna have two talks today. First one up is Yuk Chun, who will be telling us about salt planets, and then the second one we'll hear from quite a few people who went chasing eclipses in the second talk. So a Yuk Chun's talk is an AB rotation talk. So if you are new to the program or just not familiar with what we do here, graduate students are encouraged, actually they're required, if you are getting a PhD, a dual title PhD, to go and explore other disciplines of science that are related to astrobiology, or at least part of astrobiology. And so and once you finish that rotation, you have to give a talk. And so you have to completing that part of his rotation. If you are new to the program too, especially first years, I'm in charge of rotations. So please, if you want to start talking to me about it, that's my job. Stop by, and I'm happy to chat with you about what I think are good rotations and get you approved for it as soon as possible. So we hope that you take your rotation by the end of your third year or so, somewhere around there, ideally. So with that, I'm going to turn it over to you, sir. Please take it away.
Yeah, so hi everyone. I'm Yuk Chun. I am in the atmospheric science. Okay. Yeah, so I am a atmospheric. I study the chemistry going on in the atmosphere and how it's affecting climate, air pollutions, and sometimes astrobiology. And in these rotations, so I am kind of like changing my gears a little bit, trying to understand what is going on the other parts of this, the part that is more like less fluid, the solid part of this planet. And in this rotation project, my research advisor is Joshua Kusanson-Topton. And yeah, very excited to talk about my project this summer. Okay, so I want to start with a questions. So I am a big fan of cooking. I love cooking. I think cooking is the thing that keeps me sane over the whole graduate school. And I just over my years of kitchen experience, I realized that it's one skill that is really hard to master in cooking. Hi.
Can you maybe take out those?
Oh, my pronouns. Yeah, I use he, him pronouns. Oops. Oops. Okay. No, it's okay. Even no.
I have to stop sharing.
Okay, let's do it. Sorry. Okay, so let's talk about cooking. Anyone's love cooking here? Yeah. What do you think is the hardest things to master in cooking? No, it's very easy for you. Okay. So I think for me, it's definitely like how much salt to add to your food, like how much, the timing, and also like how to act really cool. And then so here's like my master. And I think I want to argue that like through this talk, maybe after this talk, you will agree with me, like a lot of this skill that I learned from kitchen is maybe transferable to like planetary science and astrobiology. So I want to essentially through this project, I want to understand a bit more about how sorting works on the planetary scale. So since this is a room for astrobiologists, I think I don't need to explain a lot about how important water activity is in just controlling Earth biology. So a lot of us just went to Crater Lake this past September. So we know Crater Lake is a freshwater system. There's not that much salt that's inside, but at the same time, there isn't that much nutrient. So very minimal bioactivities. And then we know there's oceans, there's quite a bit saltier. And then there's, of course, a lot of fish swimming around. There are lots of biologies. And then if you go to the saltier scale, if you go to Dead Sea, that is maybe 10 times more salty, and you will have a lot less biology going on there, even at the microbial scale. But there's still some biology. So that sea is not completely dead. It's not doing well. I mean, in terms of biology, but is there's some biology, and then to our system like gem, even before humans discover about like microbes, they already knew that by adding a lot of sugar or sometimes salt, they can preserve food. So this is one of the oldest biotechnology we have. So water activity and earth biology are really related to each other. And if you are in earth and space science, atmospheric science, or oceanography, you will know ocean salinity is also really important in controlling sea ice formations and also ultimately climate. So sea ice in Arctic is shrinking. I hope you already know about it because of the global warming. And there's a positive feedback going on. Essentially, when there's less sea ice, there will be lower albedo over the Arctic, and the sea will absorb a bit more solar energy, and this will speed up bonding. And if you go back far enough into Earth history, like we have even more extreme examples of like how sea ice feedbacks are controlling climate. We have period of time where the whole Earth is covered by ice, sea ice. These are snowball Earth period. And then we also have period like where there's essentially no sea ice on the whole planet. These are the early Eocene. In fact, like there are fossil records showing that like the alligators and also turtles were roaming around in the Arctic, which is something that I actually want to see. Like, and when you move on beyond Earth, we don't have a lot of understanding about sea ice on exoplanets, but through some climate model simulations, we can also speculate about what could be going on. For example, this is a study from Stephanie Austin at Purdue. Like she was trying to simulate the climate on Archean Earth using a global 3D climate model, Rocky 3D. So this is a simulation she did by putting 100 times more CO2 in the atmosphere and changing the global average salinity. So this is more like the control setup where they just set modern time salinity. And then you have quite a lot of sea ice formations over two poles. And one really interesting thing they found is that by changing the salinity by about 40%, 50%, you can get really different planetary climates. For example, if you decrease the salinity by 50 grams per kg, so you will get an even more glaciation over the whole Earth. But if you increase it like more to 50 grams per kg of seawater, you can get essentially ice-free Earth. And to the climate people here, this is a huge swing. Like changing the salinity by 40% is a huge swing, but to planetary science, this is quite small, like compared to the uncertainty that we know. So we already know that salinity, sea ice, climate are very important. And if you don't know, I want to tell you that chloride is controlling salinity in many water bodies. So this is a figure showing the composition of seawater and sea ice. And you can see that right now in modern Earth oceans, we have about 3.5% of salt in water. And then most of it is really just sodium chloride. So chloride contributes to about 50% of the mass in seawater. And chloride also has a lot of special chemical properties that makes it really important in controlling salinity. It has really high solubilities. It is not sensitive to changes and redox states of the ocean. It's also not so sensitive to changes in pH, at least in the neutral alkali range. And it's often the last anion to precipitate from seawater when doing evaporate formation. So chloride is the thing that stays behind to the end as the water is evaporating. So more curious facts about chloride. So chloride is not the only salt that we find on Earth. So we usually call this kind of like salty elements halogens. They include chloride, bromide, iodine, and fluorine. And I am an atmospheric chemist, and these halogen species are really important to atmospheric chemistry. So this is more related to my own PhD research. So this is a pretty well-known fact that halogens are really called a main driver for the ozone hole that we have in the 90s and the early 2000s. Here you are seeing a satellite observations of ozone around Antarctica. So this is 2020 October. It's the ozone hole season, and then you can see a hole in it. And the connection between halogen chemistry and ozone hole is pretty well established. Basically, wherever you find a high concentrations of chlorine radicals, you will see a ozone depletions. And this is because chlorine is participating in some catalytic chemistry. Essentially, they catalyze the removal of ozone. And in this reaction, you can see that like essentially in the next reaction, there's no consumption of chlorine. So chlorine, once you put it in the stratosphere, it can just stay there and keep destroying ozone. Each chlorine radical can destroy hundreds of molecules of ozone. So it's really effective in a lot of aspects in changing the atmospheric chemistry and compositions. And there's some recent studies suggesting that ozone hole could be responsible for some mass extinction event. The idea is that historical huge volcanic eruptions can put quite a bit of chlorine into the stratosphere, creating some giant ozone hole. Okay, so hopefully I've convinced that chloride salinity is really important for climate, for biology. Chloride is the main component to salinity on Earth that we usually experience. And also like chlorine can change the atmospheric composition as well. But here today, I want to talk about this missing chlorine problem, which is paradoxical. Like I already just told you, like there's just so much chlorine everywhere and they're so important. So what is the deal about like missing chlorine? So the missing chlorine problem actually happens when you look at the whole Earth, the bulk silicate Earth. Bulk silicate Earth is basically the whole Earth minus the metallic core. Okay, so geochemists can now have the techniques to understand basically kind of like compositions of the whole Earth, the solid part of it. And one way they analyze it is to compare it to chondrite. Chondrites are the starting material for Earth, and we believe most of the rocky planets. And this is a graph comparing different elements abundance and in the bulk silicate Earth and also the chondrites. So the y-axis is telling you like how relative the depletions of chloride and BSE relative to chondrite. So the lower the element is, the more depleted it is compared to chondrite. And in the x-axis is a measure of how volatile the elements is. And in this graph, there are three things that stand out, like chlorine, bromine, iodine. So one observations from years of chondrite, like research about chondrite and BSE, find that like chlorine content in BSE is 10 to 100 times more depleted than the starting material, the Ci chondrite. And halogens, bromine and iodine, like these three elements are especially depleted, even compared to elements with similar volatility. So you can say that it's true that a lot of elements get more depleted as if they are more volatile, but like chlorine, bromine, iodine is like stand out from the main trends. So this is quite weird. And another fact is that like the fluorine to chlorine ratio, if you compare these two halogens, fluorine and chlorine, like they also have a super chondritic ratio, which is also difficult to explain. And all this implies that there's some processes selectively remove halogens from the bulk silicate Earth. Somehow you have to get rid of 90% of chlorine in the starting material to explain these observations. And I think this is really important. So I want us to imagine like a alternative Earth. So this is not just a trivia to me, and I think this is very important to astrobiology because think about the Earth that we are living right now. So we have oceans that we can swim on it. We need effort to swim in the ocean, and there's sometimes shark chasing you. And we have the biology that we know, like that live in the oceans. We have the ozone layer. We have seasonal sea ice coverage to regulate the climate. But what if the chlorine left behind? Yeah, so you have basically you don't need to swim. You can just throw in the sea. Basically, you don't have to pay for like tanning. You can just go outside and you'll be gorgeous. And in terms of biology, maybe Earth would adapt like a biological system that looks more like hypersalient lakes that we see in some isolated part of the world. And yeah, like also alligator maybe just roaming around in the Arctic watching not the northern lights. So it's quite exciting, but it's not the world that we are living in. So I want to make sense of it, like how we got here to Earth, like how could we remove the initial chlorine that we see in the chondrite, the building material of Earth. So my research question here is to see like whether hydrodynamic escape can remove significant amounts of chlorine on early Earth. So hydrodynamic escape is a mechanism for atmospheric removal that happens on young rocky planets. So during the early age of rocket planets, they are really warm, really hot, and oftentimes they call magma ocean. The whole surface melts and form a magma. And a lot of time they have an atmosphere that is really rich in hydrogens. Sometimes it's because of interaction with the magma, sometimes because it acquires a lot of hydrogen from the nebula. So they have a lot of hydrogen-rich atmosphere. And one thing like the young sun does is it emits a lot of UV and X-ray. And this is because like young suns like are spinning really fast, and they can when they're rotating really fast, there are lots of magnetic activities causing a lot of UV and X-ray emissions. And these UV and X-ray emissions can cause the hydrodynamic escapes of hydrogen, essentially pushing a lot of hydrogen into space. And this is a process, like, although I'm an atmospheric scientist, but like this is a process that I never learned from my classes. Like, it's kind of like something that we never talk about. It's traditionally something more in the astronomy territory. Like, in fact, some of the earliest simulations or solutions came from the study of solar photosphere. And this is something that I learned and I have to learn and also just went through to teach myself about this during these rotations. And okay, so hydrogen is escaping to space like really fast. At the same time, it can bring some heavy elements with it. So this is during the hydrodynamic escape, like when hydrogen is leaving the atmosphere, it can actually put some momentum to like the heavier elements and sometimes drag them along with them to space if the flux is large enough. So there's a simple schematic showing how hydrodynamic escape works. And if you look at it at the more like the look at it at more like time series, how does it work over time? So when hydrogen escape usually start when the nebula start to disappear and then become transparent to X-ray and UV. And then during that time, you also have lots of reactions going on the Earth, the whole magma, and you have the whole liquid magma oceans, and then you have usually a really thick hydrogen atmosphere. And as time goes by, like hydrogen atmosphere is escaping the planets, and then you also have the magma ocean solid, like becoming a solid. And this is the process that I want to model. I want to essentially, especially I want to understand like during this process, like how much chlorine partition into the atmosphere, escape the magma ocean and go into the atmosphere, and also how much of it can escape to space through hydrodynamic wind on early Earth. So to do that, we cannot do experiment like easily, like this is magma oceans, and we are on present day Earth. So I need to use model. And this is the model that I use a lot, is Pacman-P. So this is a model developed by Josh. And this a model try to simulate the atmosphere, the crust and the mantle, like how they evolve over time on young rocky planet. And what it does is like it simulates all these physical geochemical processes, and it also predicts the inventories of major elements like iron, carbon, hydrogens, and oxygens in magma oceans and also in the atmosphere, and also the escapes. And it handled the partitions of volatile between the magma oceans and the atmosphere. And it has been used to study TRAPPIST-1 planet Earth, Venus, through Monte Carlo approach. It's easy to do an experiment changing like parameters using models like that. So in this project, I use Pacman-P to simulate possible atmospheres and magma oceans compositions and conditions on early Earth. On top of Pacman-P, I developed a module called GHOST, Global Hydrogen Outgas and Escape Simulation Tools. And so what GHOST that is, I'm using a nested model approach. Essentially, I'm using the outputs from Pacman-P to use it as the boundary conditions for my model. And then I use this model, use this model and then put my own variations related to halogens to run my simulations. And this is a simplification that helps a lot with instead of like running a fully coupled model, adding more species that affect the magma oceans, I am essentially trying to control it, try to simplify problems. And here, the assumption I'm making is that hydrogens are minor enough that they are not affecting the evolutions of most of the atmosphere and also the magma ocean. So under these assumptions, I can do a lot of work even without messing the main model, the Pacman model up. And so for hydrodynamic escape, I'm using an energy-based parameterizations. I'm using some experimental data for halogen solubility and magma melt, and also Bridgmanite, essentially the mantle mineral crystal. And then what Pacman-P does is changing a lot of parameters and then different initial conditions to see what kind of planet you can get. So when it's doing simulation, not all of them ends up like Earths. So I select a subset of it that resembles Earth to some extent. I picked model trajectories that reach a mantle state that was within 1 FMQ. I'm also picking the subset that has ocean that at least one Earth ocean in the whole planet. And then I'm also picking runs that have CO2 and carbon dioxide and CO2, I think smaller than, there's a typo, smaller than 300 bars. And I'm assuming hydrogen content, initial hydrogen content that's similar to some observed CK chondrite average. So let's look at the simulation results. So this is just one case that I want to show you, though this is number 191. The number is not important, just one of the case. Here you can see that, the color is really bad. Okay, so imagine, so you can see a few lines here. They're telling you, they're showing the chlorine mass in each reservoir. And then the magma ocean phase here, which you cannot see, is before the vertical line. Okay, can you see that jump? Basically, that jump is the crystallizations of the magma ocean. After that, there's no magma ocean anymore. And you can see different, basically what is happening here is during the crystallizations, a lot of the chlorine is leaving the magma ocean, going to the solar mantle. And then some of it, the blue line is surface, which means both the atmosphere and the ocean. So some of it going to the atmosphere, the ocean, and tiny bit of it, you can see a really small drop there. And this is escape. So some of it, tiny bit of it can escape the whole Earth and then go to space. Yeah, so magma ocean lasts pretty short time, about 500,000 years. And then in this simulations, the model predicts that there's not enough water at the surface. There is still one ocean of water in the whole planet, but not enough in the surface to form liquid oceans. And this is a good thing for escape because the hydrogen can just stay around and then contribute to hydrogen escape. So the model predicts that about 0.23 of Earth oceans of chlorine just escaped to space, 0.03. So it's not a lot, and I will show more cases later. And you can see pretty similar pattern for fluorine as well. So this is fluorine, and this is essentially the same plot. And yeah, same plot, but I want to show you what is going on in the model in the atmosphere. So there are few lines here. The biggest drop you can see is hydrogen. Hydrogen is escaping really quickly because of hydrogen escape. And then the other two lines that I want you to look at is the green line, the red line. They are showing the change in the atmospheric concentration of chlorine in the simulation. You can see a tiny drop of it as hydrogen escaping is also taking a bit of chlorine and more chlorine out to space. So the change in fluorine is bigger because fluorine is lighter than chlorine, so it's easier to escape for that. Another case that I want to show is, so the case that I just showed are pretty dry. Like we don't even have a ocean that form at the surface. It's not that similar to Earth. But I want to show you a case that is maybe similar to Earth a little bit. Again, like the color is not good on the screen, but imagine like after the vertical green line, so there's some blue shaded area showing that like there's some liquid ocean formed there. And what it does to the simulation is that yeah, so here what you're seeing here is the water ocean formed pretty quickly after the magma ocean is gone, just within 1 billion years. Like you already have a water oceans. And after water ocean formed at the surface, I argue that chlorine and fluorine escape will stop because they are usually really soluble. Once you have oceans, you will dissolve most of it. And there will be fairly little chlorine and fluorine in the atmosphere, just like what we have today. Like there's not like a lot of HCl gas hanging around in the atmosphere. And in this case, when you have ocean formation like that, we have even less chlorine escape to space. So now it's about 2 to the 10 to the negative 6. Really, really tiny amounts of chlorine escapes. So I just show you one case, but because this is a model simulation, I can run for a lot of different conditions. So these are more cases, like each dot is like one time series that I just showed you. And here in this plot, I want to show you like how XUV string is affecting chlorine escape. So the x-axis, the y-axis in this plot are the amounts of chlorine lost to space, and the x-axis here is the stellar XUV saturation time. Is telling you about like how large the XUV flux we have from the stars that in our model. So you can see some correlations between these two variables. Like when you have stronger XUV, you will have more escape. And another factor, another parameter that control in the model is the XUV hitting efficiency. So when you have high efficiency, more escape. So the story here is very easy, like stronger XUV, more escape. This is like a really, something that we expected, but we just showed that through this quantitative model as well. Another pretty interesting story that we find is like the amount of initial water content on planets can also affect escape of chlorine. So in this plot, you can see, x-axis this time is initial planet water. It's also a 3 parameters that we explore in the model. And when you assume like in this, first of all, when you have low initial water content, if you have less than 3 ocean water on the planet, the more water you have, usually the more escape you will see in chlorine. This is because water in this scenario control the amount of hydrogen in the atmosphere. So more initial water, more hydrogen escape, more chlorine loss. But once you have the formation of H2O, when you have more water in the planet, in the model, they would just form an ocean, and then they would just dissolve all the HCl and then HF in the atmosphere and basically just stop the escape. And yeah, so yeah, formation of H2O water and then very quick removal of Cl and F, and then stop the chlorine escapes. And if you look at the ground pictures, so this is a plot, perhaps plotting the same thing but on different scale. So here, the y-axis that I'm showing you is the final chlorine mass in the bauxite earth, shown in my model. And then there are two horizontal lines. One, the dotted line is like the initial chlorine mass that I assume in the model. And the solid line is like the present day BSE chlorine context. And what you can see here is that our model predicts very minimal escape. So like, although you can still lose about maybe 0.2, 0.6, 0.8 ocean chlorine, but in the grand scheme of things, it's not very that important. Like this escape is not changing the planetary budget that much. And our findings are consistent with previous speculations through the geochemical analysis. Previously, people studied isotopes, and also they were making arguments by saying how budgets of chlorine are related to other elements on Earth, and they make the same argument. But we show that through this modeling approach. Yeah, so some other ideas about how initial hydrogen can leave rocky planet is through impact erosions. Could be when there are other impactors hitting Earth, it can take away quite a bit of atmosphere as well. But the problem is that it can also bring volatile to the planet. So it's hard to tell. We need to do more modeling. And yeah, so another idea is that could be possible for removing like the initial chlorine is just make the planet smaller, less massive. And atmospheric escape are usually much more efficient on less massive planets. So just instead of like letting the escape happens on Earth, maybe if model smaller planets decimal, like we can get more escape, maybe make it closer to the observations. And another idea that is in the literature is maybe the extra chlorine that we see in the chondrite went into the metal core during the formations. There are some limited experimental studies showing that this might be possible. And yeah, the end is there's also some studies. Some people in the field just think that like all the other published measurements of halogens in chondrite are wrong. Essentially, they're saying that it's all contaminations. Everything that were measured in the past are contamination. Only their method is correct. So this is also possible. Maybe there's no missing chlorine. It's just like all contaminations. All right. Yeah, fun thing I did. Anyone know? Yeah, Space Needle. Yeah, I did my rotation in Seattle and in this summer, which is very different from most students. I think they usually go to other places. And I want to say I have a really fun time here, like doing it here. I think just I'm just so I think yeah, I can talk more about it maybe later. But I think just our UWAB program has so many great scientists, and every time I talk to a faculty, I feel like I can see a rotation program with them, and I'm so happy that I got to work with Josh, and it went really well. But at the same time, I'm also very happy. Like I can stay in Seattle enjoying summer. I don't have to worry about where to live the next week. Don't have to like go to Craigslist to message strangers to find a sublet. And yeah, not sacrificing my relationship with friends, partners. So it's great. I recommend it. Talk to me more if you want to do it. So summary, understanding the planetary inventory of chlorine is very important for ocean climate, atmospheric chemistry, biology. present day BSE seems to be really depleted in halogens compared to contrast. And we use a model to actually quantify the amounts of chlorine that can be lost to space through hydrodynamic escapes on young rocky planets. And we found that like hydrodynamic escape is really inefficient in removing chlorine and fluorine on early Earth, even under pre-extreme scenarios that we tested. So big shout out to Josh, great mentor. Highly recommend PacManP is like really great model if you want to use it for harm. Yeah, it's great. And then the AB program, Lisa, Rory, thank you, like very last minute proposal. And then yeah, I also talked to Stephanie Olsen, Bruce Fradley, Katharina Lourdes at Wash U, and then finally Beyonce. Okay.
All right. That's time for questions, but
Oh, okay.
yeah,
Yeah.
so, feel free to catch up next time. So can we get the next crew up?
Sorry for the people on Zoom. The laptop just disconnected, but we're gonna connect the next laptop and plug in the owl. So just give us 1 second. Okay. Where's the owl?
It's selected, I think. Echo canceling.
Oh, I see it. I see it. Okay, let's just make sure this works. I would like. Do you have to enable video? Oh, I see. Ah, there it is. Okay, and then just try sharing your screen. So if you don't do the entire screen, it will get weird.
Oh.
I do know that. I was taught that in my training. Of which was.
So just share the
there was
entire
very
screen.
I got the notes from that. Yeah. Okay, and let me go make sure that it looks okay.
If you go over to the more, you can hide media controls. All right, great. All right, we're a little bit behind schedule here, but I'm excited for this next talk. We're gonna hear all about our intrepid Eclipse chasers from earlier this year. So since we're running behind, I'm just gonna turn it over to you all and hear all about the great trip.
All right, well, hello, everyone. A group of us from ESS had the amazing opportunity to go see the solar eclipse back in April. And we're just here today to tell you a bit about it because we could not have done this without the support of the astrobiology program. So we're very thankful. And so this is us just kind of giving back and telling us how it went. Okay, just to kind of introduce you guys to the team. So there's Ula, she studies exoplanetary. We're all from ESS. And then there's me, I study Venus evolution. Andrew does Mars aqueous geochemistry. Not here today is Alyssa. She is also in ESS, but not in astrobiology. She does geophysics. And then Batiste is the person who was the head professor of the entire trip. He thought of the idea. And the last person is actually our documentary filmmaker who we had the opportunity to work with. She came with us on the trip and she got to film the experience. And we won't show the whole documentary, but we'll show some relevant clips throughout this presentation that we think were really cool. And yeah, we're just excited that we could capture this cool opportunity. And our motivation for the solar eclipse is, well, one, it's super cool. And that was definitely me during the 2017 eclipse. I thought like seeing 91% was just fine. But you really do see some fascinating features, especially for this eclipse. This is the one that happened. That was the last solar eclipse that'll happen on the North American continent for about the next 20 years. And the sun was also reaching its maximum peak activity in its 11-year cycle. So we were really excited to see some super cool prominences and features around the corona.
Yeah, so we had the opportunity to take along some really sophisticated, great equipment. My favorite piece was obviously the telescope. So this was a Lunt solar system, universal 80mm aperture telescope, modular telescope. So it had these double stack H alpha filters that you could remove. And so we actually had multiple pressure tune filters, which just allowed us to get these incredible images that you'll see later in this talk. As kind of a selfish plug, because I love these people, if anybody is interested in equipment or needs equipment for UW related activities, Cloudbreak Optics, I highly recommend. They're located in Ballard. They're great. Matt Dahl is an amazing person to ask any questions about amateur astronomy technology. So we were able to mount this on a motorized mount, set up solar tracking, and that's how we got such a great time lapse of the eclipse itself. So this was purchased originally for ESS 102. So that's a class in our department focused on space and space exploration. But we've also had the opportunity to get this outside of the classroom in other ways. We've used it for some outreach activities at Birchie Elementary School in Eastlake. We had the opportunity to teach some lessons. And then we also use this for the ESS open house.
Okay, so we are considering going to see the 2026 solar eclipse in Spain. And so because we're thinking astrobiology could be even more involved since it's a national trip, we're just going through kind of like how to plan a solar eclipse trip in these slides. So this is a map of the increase in activity surrounding the 2024 eclipse in April. This is the path of totality it went through, starting in Texas, going all the way to Maine. And the darker areas are places that, yeah, like just way more people were visiting to go see it, big population centers, big cities. So that red circle is actually where we went. That was part of the consideration, is instead of going to, for example, Texas, where most people went, I'd say, we picked Missouri and Arkansas border because in that circle, you see the color is much lighter, and it was true. There was no activity where we were. It was really in the middle of nowhere, but that was a benefit, honestly, because we didn't want that to happen. Traffic, especially when you're having airplanes to consider, flights to catch, it can really make like it could be a detriment to your trip. And the 2017 eclipse taught a lot of people that it can get really bad. And there's also, I included a map of the eclipse traffic, and yeah, it got pretty severe. But because we went up near the border of Missouri and Arkansas, we actually had zero traffic whatsoever, both going there and leaving it, because we had planned to just completely skip high population centers. And more importantly, though, you need to plan for weather. So you can only do the best you can leading up to it. Weather is hard to track, but we did have some ideas of what the cloud coverage would look like. And so not only did we pick a location that was great for population, we picked a location where we could kind of move around the path of totality as we got new information about the weather and the cloud forecast. So we actually did learn that our original spot we wanted to go to was going to be very cloudy. So we had the opportunity to move to a different location because we were centered like in that Missouri, Arkansas area. So we could kind of pick where to go. And yeah, you have to be prepared to make those last minute decisions, unfortunately, because you never know how the clouds are going to move the day of and even the hour of. And this is how we got there. To kind of overview how we did this. We landed in Kansas City, and then it was about a 3-hour drive to Springfield. And because we were centered in Springfield, not quite in the path of totality, we had the opportunity, I think we originally wanted to go like this way, but that didn't work out. So instead we changed course and went towards Arkansas instead of viewing it in Missouri. So our location allowed us to be a bit more mobile about our decisions.
Yeah, in the interest of time, I'll go quickly through this, but we didn't just see the eclipse. We also got to experience the beautiful geology of southern Missouri and northern Arkansas. Basically, there's a lot of limestone out there, and so we got to take the tour of some caves. And the one we went to is called Crystal Caves. One interesting thing that we saw, in addition to fossils, which has an astrobiology connection, seeing evidence of past life on Earth, we also saw helictites. I forget how to pronounce that. This is in the bottom right there, or bottom left. And that's when a stalactite grows at an angle that is not vertical. And that usually there's still kind of an open debate about how exactly that happens. But I think the leading theory is that there's capillary action that pulls some of that dripping to a non-vertical angle. So you get these like weird shapes, and we got to see some of those. I'm gonna skip the video in interest of time.
Bye,
Oh.
now, mine's.
But there's limestone caves. It was really cool.
I'm gonna skip through this too. Like basically, we just to kind of again emphasize that like our path was we decided to take that pathway into it. I think we can skip through this one mostly, and this part. Oh no, brace your ears. This is
I think so. So, but yeah, this is just to emphasize again, these are cloud coverage forecasts from the morning of the day of the eclipse. So we were really just like keeping track of the forecasting up until the very last minute, like up until a couple hours until totality to see if we would need to move locations really last minute. Yeah.
Okay, now the exciting part is eventually we thankfully did make it to a spot that was kind of like this 1-2 mile radius where there wasn't going to be clouds, and we got there. It was ended up being Calico Rock, Arkansas, and we decided to pick this place by the river. It was super pretty, and one of the benefits though is yes, we were in the middle of nowhere, but we actually were in quite a small town. So as you can see, they knew it was coming. They were excited. The churches were getting ready. But the other great opportunity is that there was just a lot of locals where we decided to go. And one thing that was really special to me is a lot of people, including like a lot of kids, really wanted to look through our telescope, and we were like, oh, of course, for sure, like please, like, and we got to really interact with the community around there, and they were really impressed with the telescope, and they got to see the sun in a whole new way, and so that was super special. Should we like? Okay, we can do this. We'll do this.
489 years ago, yeah. Oh, oh.
Okay, someone explain cross-setting to me, so I need to know this from Mars.
So you have like, so you have the discordance, right? Okay. Yeah. So discordance is when you have an angle between two sedimentary deposit layers. So here we have like, it appears to have like a flat one. And here we have other beddings that have an angle with it, and that is on it. That's called discordance.
So, okay, Shumway, 60-year PhD student in space sciences and astrobiology. And studying water on Mars. My specialty is looking at how water and salt and soil all intersect to potentially make liquid water possible on Mars. And driving through these dolomite limestone layers and the Ozarks and getting to talk about that and thinking about my research on Mars, where we're also seeing carbonates and thinking about what kind of environments could have deposited those, was really, really useful educational and research experience for me.
Yeah.
So we
Okay, yeah, so let's just skip to totality. So this was the big moment. We got this great image of our whole team in front of the 360-degree sunset. So basically, because the sunlight is just being blocked out from a singular point, it's not setting in the west. It looks like any direction you look, it's just the sun is setting, and that's amazing. Like, would really recommend everybody see that at some point. So we had, again, a lot of different equipment, really some standout images with the Lund telescope. And because the sun is nearing the peak of its 11-year solar activity cycle, we could see a lot of prominences. This one down here in the bottom left actually was the wishbone prominence because it stuck around for quite some time. And a lot of people were able to get some fantastic images of it. So moving on, here's a better picture of that. If you look really closely at these images, we were even able to resolve some lunar topography, which is super unique to this method of image stacking and data acquisition. So everybody, especially Batiste, was super, super proud that we were able to actually obtain data of this high quality and learn some imaging processing too along the way. And here are some images of the solar corona during totality itself. And being able to see prominences with the naked eye or through binoculars is again spectacular and incredibly unique event. And they do have these this red color invisible light.
Okay, so I don't know how to make this disappear. Go away, please. Okay. So connecting this out to beyond Earth, thinking about solar eclipses on other planets, we are really fortunate here on Earth that our moon and our sun are roughly the same apparent size in the sky, so that we have this amazing opportunity to see every many years the moon pass in front of the sun and completely block out the sun. But other planets are not so lucky. So here I'm showing in the bottom left an actual photo taken with a Mastcam Z instrument on the Perseverance rover of a Phobos transit of the sun. So that's one of Mars's moons passing in front of the sun. I don't know at what point it stops being a transit and starts being an eclipse. Maybe some astronomers can answer that afterwards. And then on the right, there's a simulation of what Saturn, what a Pandora eclipse of the sun would look like from Saturn. Then thinking about exomoons and more broadly, why do we care about this astrobiologically? Moons are really important because they can generate tidal heating, which might be able to sustain liquid water in the example of Europa and some of Jupiter's moons and potentially some of Saturn's moons as well. Ocean tides also drive wet-dry cycling on Earth. So you can think of the tide coming in, tide going out. That might be relevant to an origin of life scenarios. There are hypotheses that life needs some kind of dilution and then concentration, and wet-dry cycles potentially caused by tides have a connection there. And then moon forming impacts, like how we got our moon here on Earth, that delivers a lot of ingredients that could be good for life, but it also can be a planet-wide sterilizing event. So that's our connection to astrobio. And then to wrap up, we got a lot of amazing press coverage from this trip. Baptiste's photo made it into the Seattle Times. The University of Washington shared some clips of our trip, and we got what 7,000 likes on it. So I don't know if that's that means anything, but and we're featured in UW News. So the takeaway is not that we're popular, but that it is important and as an outreach activity. So we got to interact with local communities, bring science to places where maybe they don't have a major university around, and then also spread it more broadly on the internet and actually get people engaged in astronomy, astrobiology, and geology. And there are some links here if you want to see, or you can go and check out their social media accounts. And with that, we will wrap and take any questions.
Thank you so much. If you have questions.
I just comment that, since I went to the 2017 one and got stuck in that traffic on the way back, very impressive planning on your part.
Thank you.
Traffic scenario. And how much were you sweating the morning of, you decided you had to go?
No, Batiste had his phone in his hand for 4 hours straight, I think.
Yeah.
Some of us were more stressed than others, without naming names.
Yeah, we thought about moving from that spot at least 17 times. So it's should we stay? Should we move? But it worked out. And to the traffic point, we got up pretty early to avoid it, 4 a.m.
4 a.m.
Yeah. To make sure it didn't happen.
Yeah, well, getting there was never the problem, right? It's always getting out.
Yeah, well, it didn't end up being a problem at all, though. I think we just got really lucky that it really, really tiny town, really not a population center.
It's one of the only places in the continental US where you actually did not have cloud coverage. I think it was there in Maine, maybe?
Yeah,
But,
exactly, yeah.
Yeah,
Texas
we got
was very
super
crowded.
lucky.
I just wanted to thank you guys for like taking the initiative with Baptiste and organizing this trip and planning it all and everything like that's, and doing the outreach. It's a really amazing activity. It's great to see you guys pull it all together.
Thank you very much.
And we want to thank the astrobiology program because this couldn't have happened without astrobiology and ESS, so.
Guess we also need to thank Beyonce.
Oh, yeah, oh, we do thank Beyonce, okay.
Well, I have a question. So I know you had a few spots kind of picked out. Did you like try and coordinate with anybody local in any of those spots ahead of time to sort of maybe maximize the impact that you would have had there?
We did and failed, I think.
Oh, really?
There was Kim Bott from Tennessee, who I forgot where she's from, but I think she's an alumni. Am I
She is,
wrong?
yeah.
Yeah, we tried to do some coordinations. We did get with Matt Paul, oh, sorry, what was it?
Oh, Matt Palpon from
Yeah.
Texas A&M,
Yeah.
so we were able to meet up with some people, but no one we knew in the area. However, Batiste and I were then able to bring the telescope out like a week or so after and actually show some local kids some of the same stuff that we actually saw. Yeah, this was after the first big round of Northern Lights and we were able to see some prominences that were probably associated with the flare that caused that and show that to the kids, so that was really special.
But that is a good point. I think if we were doing this again, that might be something we would do differently, is actually reach out to local organizations ahead of time to partner with them. But I think we also wanted that maximum flexibility. So we didn't know where we were going until we were like driving there the day of.
Yeah.
Yeah, I brought up Kim Bott because that was a potential for us to save money on like hotels. She offered us a place to stay and like a collaboration with her group, but yeah, it just didn't work out.
Any other questions? Well, they live here too, so if you come up with any later, feel free to.
And there's like a 10-minute documentary that UW College of Environment made about this. So if you want to see, like, that's where that clip came from. It's on YouTube, yeah.
We were gonna show a little more, but
Yeah. Okay, thank you.
Great, good, thank you again. All right, see you all next week.